Hello everyone, welcome to today's webinar on exploring PFAS treatment solutions and their efficacy, comparing FLUORO-SORB adsorbent, GAC and ion exchange resin. My name is Ross Griffiths and I'll be chairing today's event. First of all, it's important to say I hope you're all in good health given the present situation and that you're coping with pandemic challenges around the world. And I say around the world because we have a truly global audience today and everyone's been saying hello. From around the world. We've got Western Australia, Argentina, we've got Greece, Canada, Italy, so as well as UK, US, and Canada. So welcome to you all, wherever you are. First of all, we've had a few questions about the availability of this webinar. So I can tell you this is free to attend and the recording will be made available to you all after the broadcast finishes. It'll be on the same link as you're watching it now. Just refresh it about 10 minutes afterwards and the recording will be there and you can share it with your colleagues and friends as well. But before I introduce the speakers, I just want to make everyone familiar with Crowdcast. You will see the ask a question box down at the bottom. Please direct all your questions there and we'll have a Q&A session at the end where I'll run through those. We also have polls as we go along and they're in the polls box. Our speakers will be introducing those, so look out for that box and please contribute as much as you can. And obviously the chat box that you've all been using already. So without further ado, let's introduce the speakers. So up first, we have Mike Kozak. Mike, you may have to unmic yourself, unmute yourself to say hello. But
hi, everybody.
So Mike is Vice President of CETCO Environmental Products. He will be speaking up first, but before we head out to him, we'll introduce our second speaker, who's Michael Donovan. Now, say hello, Michael.
Hi, everybody.
Fantastic. Michael is Global R&D Director, Construction Technologies at Minerals Technologies, Inc. And then last, but certainly not least, we have Chris Bellona. Now, Chris is Assistant Professor at Colorado School of Mines, and he will be coming up third in our talk. So welcome to the three of you. Now, kicking us off is going to be Mike Kozak. To actually allow him to see his slides, I'm going to have to kick Chris off until later in the presentation. So sorry about that, Chris, but we'll get you back up in a little bit. Okay, so I'm just going to share my screen now, and we can begin with the presentation. Okay, I'll make you a bit smaller there, Michael.
There we go.
Nope, I've made him big. My bad. So, Mike, over to you.
Great. Could you go to slide 2?
I can.
Good day, everybody. My name is Mike Kozak. I am the Vice President of CETCO Environmental Products and Building Materials. I wanted to take just a second and give you a little bit of background about our company. CETCO is a subsidiary of Minerals Technology Incorporated, MTI. We are a publicly traded New York Stock Exchange listed company that employs over 3,600 people around the world. We currently operate in 35 countries. We have 158 production locations, and most importantly, for what we're talking about today, we operate 12 R&D centers around the world where we look at sophisticated environmental and construction problems and develop new technologies and new products that allow us to address those issues. Our company does about $2 billion in revenue every year and has a firm commitment to continuing to develop mineral-based resource technologies into products to assist various issues that we come across around the world. And that's why we're here today to talk about PFAS. Ross, if you could advance the slide for us. I also wanted to mention that besides our PFAS remediation products, CETCO also manufactures a number of other products for both the environmental industry as well as the construction field. These center around sodium bentonite-based liners for containment of various leachates and contaminants. We are very prominent in the vapor intrusion mitigation industry, as well as containment of various contaminants for the remediation and environmental cleanup industry. The CETCO also manufactures a number of products that are used in what we call building materials, and most of these center around commercial waterproofing and vapor intrusion products as well. Ross, if you could hit the slide. So I'm very excited. I'm new with the company, and this is the first webinar that I've participated in. We have a great lineup today. I look forward to hearing from Mike Donovan. He's our R&D Director for CETCO and is being joined by Chris Bellona, who is one of our great university partners from the Colorado School of Mines. And they're going to share their research study on PFAS treatment options and what we are so excited about when it comes to our FLUORO-SORB adsorbent. They'll be reviewing their research findings along with some very interesting field pilot studies that are currently ongoing, and really look forward to hearing what they have to say, as well as the questions that will come from all of you, our audience. Thank you, everybody, for allowing me to introduce Chris and Mike. And guys, I'm going to turn it over to you.
Okay, can everyone hear me?
Sure, we can hear you, Mike.
Great. Hi, I'm Mike Donovan. I'm located in one of the 12 research centers in the suburbs of Chicago. And I'm going to start out my section with a poll. So the question to everyone is, what treatment options are you considering for upcoming PFAS remediation efforts? FLUORO-SORB, granular activated carbon, ion exchange, reverse osmosis, chemical oxidation, other, or I'm not working on a PFAS project. So please answer the question, and I think we'll jump to the next slide, please. So there's currently a lot of different ways folks are considering to treat PFAS. And you can look at them in filtration or sorbent types of media as ways to do that work. And what we've done is kind of pull together a comparison of the three major sorbent medias that are used today. So FLUORO-SORB adsorbent media is similar to GAC, and it's a granular media, and it can be used in filtration vessels. And there's a little bit of difference between the two media for filtration in that FLUORO-SORB can actually be used with a lower empty bed contact time. And in fact, it's similar to an exchange resin, somewhere between 2 and 5 minutes. If you look at the cost relative to other media, FLUORO-SORB is the lowest cost. And we have data, which I'll show you in a minute, to demonstrate that we are the most robust media to the impact of co-contaminants. And we can also be used for in situ applications like mixtures with cement. So I'll share that data at the end of my talk. So there are other treatment options. There's some newer things like chemical oxidation and even biodegradation, where you're actually trying to destroy the PFAS molecules. And another common technique is reverse osmosis. And that's typically used in things like wastewater treatment plants, where there may be other contaminants that you have to remove as well. Next slide, please. So what is FLUORO-SORB? So it's a proprietary mineral-based media, and we take a naturally occurring mineral and we surface treat it to absorb hydrophobic compounds like PFAS. We launched the product about a year ago, in fact, May of 2019. It's certified for use with drinking water, and it's manufactured in an ISO 9001 facility in the United States. Next slide. So what can you do with FLUORO-SORB? Well, it's very versatile. You can use it in filtration vessels. You can use it in various scenarios if you want to treat contaminated groundwater. You can use it as a permeable reactive barrier. Think of, if you look at the upper right-hand part of the slide, that gray wall, it could be used basically to absorb the contaminants from the groundwater itself, or you can mix it at the source. So if you have a source zone that's contributing to groundwater contamination, you can mix it directly into the soil. And we also sell products that deliver the media in a needle punched reactive core mat, so you can cap sediments with a technology like that. Next slide, please. So FLUORO-SORB comes in 4 different types, and generally it's different particle sizes. We do have one media that's a mixture with anthracite, and that's FLUORO-SORB 300. But generally the differences are particle size, and we can do that. We can do different applications with these different particle sizes. Typically, our FLUORO-SORB 100 product is the smallest particle size. Its particle size ranges from 0.1 millimeter up to 1 millimeter. and it's the most dense of the media, and it has the lowest hydraulic conductivity. And we've seen it used in in-situ stabilization and also DAF applications. FLUORO-SORB 200 is a little bit bigger in grain size. It ranges from 0.5 millimeters to 1 millimeter, and it can be used in pump and treat. And that media we also mix with, as I mentioned, anthracite, and that's used in situations where you might have high organics. Because our media absorbs organic compounds, we put the anthracite in there to maintain high hydraulic conductivity. And then lastly, FLUORO-SORB 400 is a larger media, and the particle sizes is the biggest, and it ranges from 0.5 millimeters up to 5 millimeters. Next slide, please. So here, time for another poll. If you are engaged in a PFAS project, how do you dispose of your spent media? Incineration, disposal in a landfill? Do you regenerate and reuse it? Maybe there's some other option, or I'm not currently working in a PFAS project. Okay, appreciate your responses to that question. Next slide, please, Ross. So as I mentioned, we've been working with, as Mike mentioned, we've been working with a few different universities. And this particular study was done at McGill University in Montreal. And we were looking at the impact of FLUORO-SORB on treating AFFF impacted soils. So what we did was we took multiple samples from a couple different sites, one in Canada and one in the US, and these were Air Force bases used by the military. And you can see that there's slight differences in the types of soils that were at the sites. And you can see a sort of a big difference in the concentrations of PFAS in the soil. So ranging from 60,000 nanograms per gram all the way down to 1,800 nanograms per gram. Next slide, please. So I want to summarize, some of the results that they found. What we saw was we can get significant reduction of PFAS in the range of 95 to 99% reduction with as little as half a weight percent treatment of the soil. It works really well for ionic PFAS molecules, but if you have non-ionic PFAS compounds, it doesn't work as well. You get 70% to 99% removal. But if you want to treat those compounds, you simply have to add more of the media. Generally, we do better than GAC for most compounds, particularly PFOS. And really, what we found is if you add enough FLUORO-SORB, you can treat the soil to reach drinking water level, the drinking water advisory levels on a leaching study. So, but it's soil dependent. If you have higher concentrations of PFAS in the soil, you may have to add more. Next slide, please. So the next thing that they did was at one of the sites, we were able to collect large volumes of the groundwater. And in this study, we looked at treating the water with the same media. So we looked at FLUORO-SORB 200, a granular activated carbon, a hardwood biochar, and an ion exchange resin. Next slide. So this data compares the different media. And we picked out some select compounds, PFOA, PFOS, and then we looked at the total PFAS composition after leaching. So this experiment was done by adding 40 milligrams of groundwater with 500 milliliters of groundwater. And one of the key things that you have to note is it takes some time to reach full equilibrium. So we recommend if you do an isotherm study to reach full equilibrium, you have to put it on the shaker for 7 days. So you can see the comparison with the different media. So our FLUORO-SORB 200 media is the green bar, which has comparable performance to the ion exchange resin, which is the orange bar. Looking at granular activated carbon and biochar, they had lower removal efficiencies for these compounds. So we really on an efficiency basis are very similar to ion exchange resin. Next slide, please. So the next thing we did was we asked the question, what happens if there's other co-contaminants in the groundwater? How would that affect the performance of FLUORO-SORB? So we picked two compounds, again, PFOA and PFOS, and we saw a little bit different response for each one of the compounds adding in these co-contaminants. So we looked at naturally occurring organic matter, and these are humates. We looked at adding diesel, 1,4-dioxane, BTEX, and TCE. And really it was sort of impressive that the FLUORO-SORB kind of ignored most of the organic compounds, and where we saw only a 12 to 4% reduction in the removal efficiency. The biggest impact was seen by the naturally occurring organic matter, but if you compare that to GAC, that's actually a really good result. We were only reduced in efficiency to somewhere around 42 to 24%. Next slide, please. So this is the isotherm. This is kind of an interesting feature for FLUORO-SORB, is that typically for isotherms, you see a linear response with the dosage of the media into a groundwater sample. But for FLUORO-SORB, you see this sigmoidal curve. So at some point in the treatment, we actually see higher absorption of the media. And we have data that suggests that because of the nature of our media, the media can expand and absorb more of the compound. So in order to push it to full absorption, you have to really be patient and look at a lot of samples. But what we found is the absorption capacity, the full absorption capacity, can range somewhere between 14 to 31 milligrams per gram. And that is, a pretty, if you compare to other media like GAC, is, the absorption capacity is a lot less. It's less than 1 milligram per gram. And also the absorption capacity is dependent on the molecular weight. So depending on the PFAS composition, you might see in total slightly different absorption capacities. Next slide, please. So to summarize the groundwater study, generally it's superior to granular activated carbon, similar to ion exchange. And we found it to be very robust against different types of groundwater conditions. And if you're interested, this work should be published in the coming months. So we're happy to share that study with anybody that needs to see it. Next slide. Switching gears a little bit, I'm going to present some of the research that was done at the University of Texas at Austin. This was done with Professor Shadi Al-Muhtar. And this study, I have a motions activated light switch. So sorry, now I'm back. So what we wanted to do was look at treating a source zone and doing in situ stabilization with mixtures with cement. And this is typically used when you have to have some bearing capacity of the soil. Next slide. So a lot of our work was actually based off some initial work done by Peter Storch, and this was presented back in 2017 when we were still developing the product. And Peter compared our media with another common media that's on the market, which is a blend of activated carbon and gibbsite. And he did some control samples with just soil and cement. So what you're seeing is some leaching data where Peter mixed the different medias in the soil. And in this particular study, he was looking at, for our media, 5 weight percent FLUORO-SORB and 10% Portland cement. And so what he found was that the soil by itself, if you try to do a leaching study, you saw 228 ppm in the leaching water. Very, very high concentrations of PFAS in the soil. And next, he looked at adding in cement, which reduced the leachability by a couple order of magnitudes. But still, you could see the concentrations was somewhere around 1 ppm. The other material that he used, the gibbsite carbon blend, was somewhat effective in the soil by itself. But however, when you added cement, you saw a 2 order of magnitude increase in the leaching, which was kind of interesting. It kind of suggests that the cement has a negative interaction with this particular type of treatment. Whereas our FLUORO-SORB product, we saw the lowest leaching around 0.3 ppm. And with adding cement, we saw a reduction by an order of magnitude. So this study kind of demonstrated that adding cement and FLUORO-SORB kind of works together to help solve the problem. And this was installed in 2018 and is undergoing annual SPLP leaching studies. So based on that work, we engaged the University of Texas at Austin and wanted to do, next slide, please. Wanted to do a study of that soil that I mentioned that was collected in the US. So this was an Air Force base. It was used throughout the Cold War. A lot of firefighting training and actual fires that occurred at the site. So you see a wide range of PFAS compounds in the soil. We only analyzed for 28 compounds. There could be a lot more, but you can see that composition is highly dominated by some of the longer chain PFAS molecules like PFOS, FOSA, which is a sulfonamide, and the PFOA. Next slide, please. So with the university, we did a design of experiments, and we wanted to look at the effect of the concentration of FLUORO-SORB in the soil, as well as the loading of cement. And what we wanted to do is tolerance not only the strength performance, but the removal efficiency. So the gray circles at the top of the chart indicate cement alone. There's no FLUORO-SORB. So we did see about an order of magnitude reduction in the concentration of the leaching using the EPA 1313 method. And so what we did was we wanted to understand and tolerance the lowest amount of FLUORO-SORB that you need for this particular type of soil and cement to reach leaching levels that would meet drinking water standards. So we looked at 1%, 3%, 5%, and 8% the FLUORO-SORB in mixtures with different ranges of cement. And what we found was there is a slight curvature at low FLUORO-SORB levels. As you add more cement, you liberate more of the PFAS molecules, which has been seen before, that raising the pH can liberate PFAS compounds. But in order to be sure that you're less than the drinking water standards, we recommend that 5% FLUORO-SORB is the minimum addition rate. And again, this is dependent on the soil. We've seen other soils with lower concentrations of PFAS, and you can add less FLUORO-SORB and meet those drinking water standards. Next slide, please. So in summary, one of the things that we were able to do is reach low concentrations with various mixed designs. Portland cement by itself was not effective in just hydraulically isolating the soil to treat PFAS. And some of the compounds that were in there were detected at higher levels in the soil, and those adding in cement can liberate some of those compounds. So you have to be careful and make sure you're looking at all the compounds that could potentially exist in the soil. And we're recommending at least 5% Portland cement and 5% FLUORO-SORB. We give you a pretty robust mixed design. And I think this is my final slide. Next slide, please. So I'm going to end with a poll. So one of the questions that we have for everybody is, how do you base your media treatment selection? The manufacturer says it's going to work really well. You've used it before on other types of treatments and you're familiar with the process. It's readily available and it's the first thing that kind of jumps to mind. It's recyclable and reusable. Or are there other reasons that you pick a media? Or again, I'm not currently working on a PFAS project. Next slide. All right. I think that's the end of my section.
Yeah. Okay. Thank you very much. I'm just going to get Chris back on the screen. I think now would actually be a really good time just to summarize some of the earlier polls, if you were keen, Mike. What treatment options are you considering for your upcoming PFAS remediation efforts? We got 21% saying granular activated carbon. 52% are not currently working on a PFAS project. 12% said ion exchange resin. So that's interesting. If engaged in PFAS projects, how do you dispose of your spent media? 55% said they weren't working on a project, but 27% said incineration, 11% landfill. Interesting. So we now have Chris. So I'm just going to allow Chris to, I don't need to maximize you, Chris. If you just take it away.
All right. Can you hear me?
Yeah, we can. Yep.
All right. Well, thanks, everyone. My name is Chris Bellona. I'm an associate professor in the Department of Civil and Environmental Engineering at the Colorado School of Mines. I started working with CETCO because we've been evaluating a variety of different treatment processes for removal of PFAS from contaminated source waters, adsorbents, membranes, some destructive technologies. And as Mike had alluded to previously, they had done quite a bit of work on isotherms, so batch isotherm experiments evaluating FLUORO-SORB, and we were sort of tasked with evaluating FLUORO-SORB in a flow-through systems. So what this figure is showing is a system that was built at the Colorado School of Mines, where we had segment and column system. We were comparing primarily GAC to FLUORO-SORB, as well as looking at FLUORO-SORB as a pretreatment to GAC and ion exchange. And for these experiments, we were shipped contaminated water from a site in the United States with relatively high PFAS levels. If you summed up the total of PFAS that were quantified in these samples, we were at around 60 to 80 micrograms per liter. Next slide. So I'm not going to get into too much of the details of this experiment, but to show more of a summary slide. So what we have here on the y-axis is a sum of 8 major perfluoroalkyl acids, and this is in the effluent of the column system. And then on the x-axis, we have bed volumes processed. So GAC system was run at an empty bed contact time of about 10 minutes. And then for the FLUORO-SORB, we were focusing on a 5-minute empty bed contact time. And I'll talk a little bit more about empty bed contact time in these adsorption systems. What we found was that it took a long time to get breakthrough for the FLUORO-SORB material, specifically relative to GAC. I think there's animation on this slide if you hit. There you go. So if you look at a value that's similar to the US EPA health advisory level and the number of bed volumes processed to get to that level of breakthrough, the FLUORO-SORB during these experiments had about 4 times more water processed before we got to that health advisory level value. And I will note, you'll see a little bit of spread in the data for the FLUORO-SORB in terms of the PFAS or the perfluoroalkyl acids in the column effluent. And the reason primarily is because we are near the detection level for these PFAS. So it took a long time before we really started to see a response in the samples. But this indicates that for these experiments, you would have about a 4 times longer adsorbent life for FLUORO-SORB compared to GAC. Next slide. So Mike's been doing, and CETCO have been doing some work to kind of trying to evaluate what's the nature of the capacity and the high capacity that's often seen for FLUORO-SORB compared for PFAS removal. And he did talk a little bit about this when he was presenting adsorption isotherm results. But here we have the solid phase concentration or sorption capacity on the y-axis as a function of the equilibrium concentration, the aqueous phase concentration. And typically for isotherms experiments, you do see a leveling out of the solid phase concentration or sorption capacity as you increase the aqueous phase concentration of any solute. What's interesting with FLUORO-SORB is you typically don't see this, and you can see this inflection point that indicates that there's some increasing capacity as you load PFAS onto FLUORO-SORB, which is hypothesized to be due to the platelet structure and the fact that these platelets can expand as the FLUORO-SORB starts to absorb PFAS. Next slide. You can see the little animation there. So based on these column experiments, what we found was that FLUORO-SORB does have a higher capacity for the perfluoroalkyl acids that were evaluated, and that in some further work that I'll show a little bit of results from, so we're above the absorption capacity for GAC, and it's very similar to ion exchange. And Mike showed some figures earlier that indicated that FLUORO-SORB isn't significantly impacted from other background analytes, maybe a little bit by NOM, but other co-contaminants don't have a big impact on absorption capacity. Next slide. So some other work that we've been doing, Orange County Water District in Southern California has become kind of the stewards of the groundwater basin there, and they have somewhat elevated levels of PFAS compared to the notification limit for California. So they've started a pilot program where they're evaluating different technologies for the removal of the PFAS that are present in the groundwater, looking at a variety of different technologies, including adsorbents. And they're focusing on, kind of the main players, activated carbon, ion exchange, but also some more novel adsorbents, including FLUORO-SORB and some other compounds. So there's a big piloting program going on in Orange County, and we've been doing some kind of screening work to evaluate PFAS removal by other adsorbents, including PFAS. So just to note that if you look at the groundwater levels of PFOA and PFOS, they are pretty low. So we're talking in the 15 to 30 nanogram per liter range. So we were shipped water from Orange County, and you can go to the next slide, to the lab where we could do some rapid small scale column tests. And I'll talk about some results in a minute, but this is a table just showing general water quality as well as PFAS levels for this groundwater. So again, we have groundwater, relatively low TDS, about 600 milligrams per liter. TOC is fairly low, about 1.5 milligrams per liter. And then you can see the levels of, here we have perfluoroalkyl acids, some shown, are generally quite low. You can go to the next slide. So at Orange County Water District, they're performing a pilot scale experiment comparing different adsorbents to one another. These are 6-inch column tests. They're running about 8 GAC products at a 10-minute empty bed contact time, comparing it to fluorine ion exchange products at 2 minutes of empty bed contact time. And then looking at some other novel adsorbents, including the FLUORO-SORB material. One thing to note is that for this study, it's been decided to run the FLUORO-SORB very similar to ion exchange in terms of empty bed contact time. So a 2-minute empty bed contact time to evaluate the performance very relative to ion exchange. And that's important in terms of the volume of media that's required to treat a given amount of water. For GAC, if you're at a 10-minute empty bed contact time, you would require 5 times more media compared to an adsorbent that was running at an empty bed contact time of 2 minutes. Go to the next slide. These are some results from rapid small scale column tests. So the idea behind a rapid small scale column test is you grind the media down to a predetermined size and run it in small column systems. And the idea here is that you can screen a wide variety of media for removal performance in a relatively quick amount of time. So this top figure on the left is showing some results from different GAC products in terms of PFOA effluent concentrations. So that's on the y-axis. And then again, on the x-axis, we have bed volumes. And these are simulated bed volumes because this was done in a rapid small scale column test setup. But you can see relative to some kind of metrics. So California has low notification levels for PFOA and PFOS around 5 to 6 nanograms per liter. And then we have kind of a baseline value of 10 nanograms per liter, and then 80% of that at 8 nanograms per liter. And from this top left figure, you can see that you typically see breakthrough of perfluoroalkyl acids in GAC systems around 60,000 bed volumes. And this is a trend that I've seen in pilot scale studies as well with contaminated groundwater. And then in the bottom, we have 2 separate experiments that were done for FLUORO-SORB. One was done at Battelle and one at the Colorado School of Mines. For the Colorado School of Mines, we were running around a 3-minute empty bed contact time, and Battelle actually did a 1 minute empty bed contact time. So in these experiments, the water is just screaming through this media. You can see we got to around 600,000 bed volumes for the FLUORO-SORB before we started to hit that 10 nanograms per liter. So about 10 times more bed volumes compared to GAC shown in the top left. I'll note that bed volumes can be a little difficult to compare when you're running a column system at different empty bed contact times. So if you assume that we had about a 3 times reduction in the empty bed contact time compared to GAC, we're still significantly processing more water before breakthrough with FLUORO-SORB. Next slide. I guess we had some animation. So this is kind of a snapshot of the performance of FLUORO-SORB in column-based systems. And Mike showed some more data from isotherm experiments. But you typically always want to evaluate whatever media you're considering with the water that you'll be trying to treat. You can have some competition from other background analytes and things like that. So CETCO encourages you to run your own trials, and they provide free samples of media, testing program, and data review input, as well as instructions on how to sample and ship. And they do quite a bit of isotherm testing as well, and have some column testing units. So if you're interested in FLUORO-SORB for treatment of a particular water, contact CETCO here. Next slide. So I think this is my last, but here's the final poll for today. So prior to today's webinar, were you aware of FLUORO-SORB adsorbent as an effective PFAS treatment solution? Yes or no? And with that, I'll turn it over to Ross.
Okay, thank you very much, Chris. We are going to go straight into our Q&A session. So let's get rid of this. We're just going to get Michael back up. I had to get rid of him because his face was in the way of the lovely slides. So, and I'm also going to get Mike Kozak as well back up. And we've had a lot of questions. I can tell you that we've had about 8 questions so far. So speakers need to strap themselves in. So I'll just invite those two while we're waiting for them to join. I will just go back through some of the poll findings that we had later on in the session. So how do you base your media treatment selection? The results of that suggested we had 24% saying that they've used it for other types of treatment and are familiar with the process. And that we had 13% who went for other, 8% went for the manufacturer says it works well on PFAS. So that's very interesting. And prior to today's webinar, were you aware of the FLUORO-SORB adsorbent as an effective PFAS solution? 38% said yes, but 61% are actually saying no. So that's very interesting. Right, let's get Mike and Michael, who have now joined us. So, Mike, I'm just going to place yours on a... Oh, there you go. He's on it already. Okay, so first, well, we've had 12 questions. Okay, so let's just get straight on to it. Question number 1. What is done with the spent FLUORO-SORB? Is it just left out in nature? And
Okay. Can you hear me?
just about. I might toggle your video just to... We're having a bit of bandwidth struggles your end, so if I toggle your video, you're still there, but you should be able to answer a bit clearer now. Oh, Michael?
Okay. Can you hear me?
We can.
Great. Oh, okay. So our media is actually designed to be left out in nature. So we're using this media to treat either source zones or contaminated plume. In the situation where you have what we call a permeable reactive barrier, or PRB, there may be a point at which you reach saturation. So it's really kind of dependent on the design engineer to determine, what the lifespan of that permeable reactor barrier needs to be. And it's meant to be left out in nature until it reaches capacity, and then you can replace it if you need to, which generally requires monitoring to know when that happens. But yes, it's designed to be mixed with soil and left there forever.
We had a few kind of follow-up questions on that. David Strange, and also we had another one a bit further down, Paul Knifley. They've asked, can it be regenerated? Can FLUORO-SORB be regenerated? We
haven't done studies to demonstrate that it can be regenerated. We don't, right now we're recommending our customers actually landfill or incinerate the media.
Okay, fantastic. What is the cost of 1 pound of FLUORO-SORB, and how does it compare to the cost of 1 pound of granular activated carbon and 1 pound of ion exchange resin?
Mike Kozak, do you want to handle that question?
I'll do my best, Mike. So my understanding is that our cost is comparable with granulated activated carbon, and that we are less expensive than ion exchange resin. The important distinction, though, is that our product's effectiveness is significantly greater. So even though the cost per pound might be the same, you're buying less FLUORO-SORB than you would be either of the other media. So from an effectiveness and total cost perspective, we think that FLUORO-SORB represents a really great value to the market.
Yeah, and I'll just give my thoughts on that. As Chris showed, you saw all those different RSS-CT curves. So in that study, there was at least 6 different activated carbons that were selected, and each one of these carbons may have a different price point, but definitely for activated carbon, you get what you pay for. And unfortunately for customers working with carbon and PFAS, generally the more expensive forms of GAC are the ones that work the best. So you can try to be cost effective with your GAC selection, but that may not help you get higher bed life if you're doing pump and treat. I don't know, Chris, do you have any thoughts on that?
No, I would agree with that.
Excellent. Someone's just popped in on the chat box. Greg, has the media been tested to NSF ANSI 61?
Yes, yeah, it's approved for use with drinking water, and it's been certified by ANSI NSF 61.
There you go, Greg. Next question from Paul. How does its structural stability compare with resins?
I guess there's a couple of ways to look at that question. In terms of resistance to degradation, it's mineral based. So these minerals are very stable at a wide range of pHs. So if there's low pH and high pH, we don't anticipate any degradation of the performance or the material itself.
Okay. Right. Next question from Brian. When you dispose of FLUORO-SORB in a landfill, will the PFAS leach out?
That's a great question. And we are actually engaging some universities like Professor Bellona at the Colorado School of Mines to start answering some of those questions. But every landfill is different. The chemistry of the leachate is different. We've done a lot of our studies using EPA leaching methods, and what we've seen is very, very low leaching once it's absorbed. You see a little bit on the first, if you do like a dynamic leaching study, you see a little bit come out in the first leach, but after that you see very little. So it's very stable. And I don't know, Chris, if you have any thoughts on leaching in different types of wastewaters.
I mean, we've kind of just started that work, but I think it is an important question to answer specifically for the stabilization work.
Okay, another kind of leachate question. Does the PFAS leach back out of the FLUORO-SORB after adsorption or saturation point has been reached?
So this, that was similar to the last question. If you do, like semi-dynamic leaching studies like EPA 1315, and you could look at even different pHs, we see very little leaching after it's absorbed.
Yeah, and in the column system, sometimes you do see this peaking phenomenon where certain perfluoroalkyl acids will come out of the column system above the influent concentration, and through our column studies, we have not seen that yet. It appears that once you reach exhaustion, you just basically have what's coming in, coming out.
Okay. Another question from Paul. He's been very active. Does FLUORO-SORB contain fluorinated materials that can desorb or otherwise raise public concerns about its content?
No, there's no. We do not intentionally add any type of fluorinated compound to the product composition. No.
Okay. Wow, this question is going to test me. From Jean-Pierre. 2 main questions. 1, what is the removal efficiency for short chain PFBA, PFBS, and for Adona C604 Gen X? 2, can it be regenerated by heat to destroy PFAS?
I guess I'll handle the first question with the short chain. I showed that in my slide before, but generally we see about 20 to 50% lower absorption with the short chains. So our material is operates based on a hydrophobic interaction with the PFAS molecules. So the longer the chain and the more hydrophobic the molecule, the better it absorbs onto the media. And it's a competition. So, but compared to things like GAC, when you're competing for the surface of the sorbent, there's only so much room. But what we found with our product is, as you saw in those isotherms, that the material can keep absorbing more and more compounds. So we are maybe not as good as the short chains as things like ion exchange resin, but we have a new media that it's in development right now that's going to rival the performance of ion exchange resin for the short chain. So we have something that our product today works very well, but we're developing some new media that is Chris is actually evaluating that media right now to actually demonstrate that.
Okay, excellent. Okay, question from Richard Sutton. It was mentioned about a needle punch system. Can you provide any more information on that and its efficacy? I have contaminated soil that is above a deep aquifer, which needs to be moved to another part of the site.
Okay, yeah, so what's really nice about our product is we can blend whatever we want together and then deliver that in a needle punch geotextile. So these products are typically 15 feet wide and 150 feet long, and they can be deployed in the field, let's say in a water body, and generally they're deployed on the surface and they're lowered to the bottom of the water body using, basically divers can help guide it in place. So we put our media over the contaminated site, almost like a Band-Aid over a wound. And we can design in different thicknesses or weights. And so we express that as a mass per unit area. So we can go a half a pound per square foot up to, a little bit over 1 to 2 pounds per square foot. And these are designed to let water flow through. So the intent is that it's not a hydraulic barrier. It's designed to allow water to penetrate and percolate through the system and absorb the contaminants. So that is something that we're working, with some other universities on some studies to demonstrate, that works in the flow rates you need to target. But that is certainly an option for PFAS and, maybe other contaminants that might also be in the aquifer.
Okay. So David Holmes asks, can you describe the mechanism by which PFAS absorbs to the FLUORO-SORB? I feel like you covered that in your last question. So we probably don't need to go into that. Michael's sensitive lights have gone off again.
Sorry, I work in an energy efficient building, and
that's good. We like that. We like that.
Yeah. So it's a hydrophobic interaction. So Chris showed the little cartoon of the PFAS molecules depositing on the surface of the platelet. So if you can take our media and actually analyze its structure using X-ray diffraction. So it's a plate-like mineral that's very platey. Each one of the platelets of the mineral is thousands of nanometers long and wide, but only 1 nanometer thick. And so imagine like a deck of playing cards, and the space in between the playing cards is where the contaminants go. So we do think that there's some ionic interaction, and that's one of the reasons why it works very well with carboxylates and sulfonated PFAS molecules. So we do think there's an electrostatic attraction as well as a hydrophobic interaction. So we treat the surface of the platelet with a very long chain hydrophobic molecule. And so we have that, it's almost like surfactants, the chains of a surfactant or a soap molecule interacting with themselves. So one of the things that was done by the University of McGill is they've actually done X-ray diffraction studies after absorption. So they drove the media to complete absorption, and they looked at the X-ray diffraction before and after, and they saw an increase in what we call the D-spacing between the platelets. So typically the D-spacing is somewhere between 23 to 30 angstroms, and that increased to around 65 to 70 angstroms. So we do actually see an increase in the distance, and that suggests that those PFAS molecules are populating the interstitial space between the platelets and then opening them up. And another thing that they're doing is they're actually using some other high energy scattering techniques to count fluorine atoms between the platelets. So they're actually able to tell how many fluorine atoms exist between those platelets. So they know, based on these studies, where the PFAS molecules are going, and it's diffusion based. So the molecules come in at the edge of the platelet and on the surface of the platelet, and they diffuse inwards. And so that's one of the reasons why when you do a shaker test, we recommend going out to at least 7 days, because the molecules time to diffuse in and reach that full absorption capacity.
Okay, there you go, David. I hope that answered that
That's a great
question. Yeah, we got another one here that you've also kind of answered, but you might want to add a little bit more. But how does FLUORO-SORB increase removal efficacy as FLUORO-SORB expands? Does it charge the PFAS?
Well, yes, we think there's some electrostatic interaction. So mineral that we work with has an overall charge on the edges, and so it's produced by an ion exchange mechanism with our particular mineral. And so there may be some material that we add that is charged that interacts with the surface of our clay that it helps, sort of accentuate the removal. So as I mentioned before, it's really efficient at long chain molecules. And I don't think I addressed the second part of the one question. So we are working with some companies that have issues with Gen X. We know it works with Gen X. Compound is a little bit different than some other molecules. So we're still in the sort of development stage and learning about how it works with Gen X. So hopefully the next time we meet, we can actually present some of the Gen X data.
I just had to toggle you there. Everyone can still hear you, but your audio gets a lot better when I toggled your video. I think you're having a slight dip in bandwidth, but we'll keep going. Okay. Bertrand Dussett says the cost of generated activated carbon is much lower. Doesn't even pose that as a question, more of a statement. I don't know if Mike wants to respond on that.
Ross, we're having some audio
I have some thoughts,
problems. Could you repeat that?
Sure. One of our delegates said that granular activated carbon is much cheaper. He didn't provide any more information on that, but I don't know if you want to respond. You don't have to if you don't want to.
Well, again, it's a difficult question to ask because we don't know exactly what grade or class of granulated activated carbon he's speaking about. But again, I would just point to my earlier answer that you have to go back and look at the efficiency data and the effectiveness of our product to be able to get a total picture of the cost effectiveness of various options.
Michael, your video seems...
Chris, do you want to comment on... Go ahead, Ross.
Sorry. Yeah, I was just going to say, Michael, do you want to comment on that, or Chris?
I've got some thoughts as well. But Chris, do you have any thoughts on that?
No, I agree with what Mike said. You really have to look at the effectiveness to understand. I mean, the cost is really going to come when you change out on media. That's going to be your big cost. So if you can operate for longer periods of time, then that's the real factor.
Yeah. For some applications, the GAC that is used for drinking water can be regenerated, but mostly that media itself ends up somewhere else. And for most drinking water applications, what the customers get is new material, and what they get back after it's used is regenerated and potentially used for other areas. For treatment systems that are looking at groundwater, where you may not have to reach drinking water standards, in that situation, they may regenerate it and use the same media over and over again. But you must appreciate that every time you regenerate the media, you lose some of the media. It burns away. And, that's, 10% of the media gets actually burned in the regeneration process. So you have to constantly buy more to maintain the same volume of media.
Okay. Katie asks, can FLUORO-SORB be used like PAC or PAC?
Yeah, well, in terms, I guess, really depends on the application. We're looking at a site that's treating surface water, and they're converting the surface water to drinking water, and they're using a dissolved air flotation process. And they're comparing that to GAC, and our media is actually outperforming the pack used at the site. And so we're in kind of late stage qualifications with our FLUORO-SORB 100 product for that.
Okay. Paul, again, he's really testing you here. How does FLUORO-SORB handle competitive binding of the anions?
That's a great question. We've seen, I guess it really depends on the site water. In one recent instance, we saw, typically we see better removal of the sulfonates. But in one instance recently, we saw better removal of the carboxylates. And so this gets into a point that Chris Bellona made, is you have to do studies based on the actual leachate, and it's good to to understand things like the concentration of PFAS itself, but there is a competition, and also there's pH effects. So it could be that the pH may be a little different, and if you are low pH, the carboxylates may become more protonated or less ionic, and then have a tendency to absorb on the material because now they're more hydrophobic. At higher pHs, we see that there's a better interaction with the sulfonates, which again kind of indicates there's an ionic interaction as well as a hydrophobic interaction. So it is a competition. Generally, the higher molecular weight compounds win, regardless of the species. But at lower molecular weight PFAS compounds, for example, like PFH, the PHX. The hexane sulfonate compounds, we see actually better performance of FLUORO-SORB for the sulfonated low molecular weight compounds than the carboxylated ones.
Okay, relating to the cost of GAC, we've actually had another comment from Bertrand who said, "What I meant is the cost of reactivated carbon is about half the cost of virgin carbon." So I got that wrong. Sorry about that, Bertrand. So, a question from George Larty Young. By adding to soil PFAS treatment, how do you determine the effect of FLUORO-SORB from the organic matter sorption?
We were hoping to get at those studies with the different sites that we looked at. So the Canadian soil was a little bit different in the mineral makeup, but they both had similar amounts of organic matter. As everyone knows, the PFAS molecules like to stick to the organic matter. And if you go back, in the future, go back and look at the slide where you see that the University of Texas study, and you see 28 different compounds. That is much different than the groundwater leachate that Chris evaluated. So what we see is that in the soil, you see more or higher concentrations of the cationic and zwitterionic PFAS compounds. So the composition of the soil is going to be different than the composition of the leachate itself. So our material does work with cationic compounds. It's not as efficient as the anionic compounds. But again, I made that comment. If you need to treat those compounds, you simply have to add more FLUORO-SORB. Okay.
Yeah, you guys okay for a couple more questions? There's just a couple more come in.
I'm okay.
Yeah. Okay, so we have a question from Simon Farr who asks, have you undertaken any longevity studies?
Not, that's more of the work that we're doing in the field. So I mentioned the site in Australia that was done in 2017. They're monitoring that every year. It was installed in 2018. So by now they'll have a couple of years worth of data. We have similar products that have been used in other applications, and these are meant to be installed and left for long periods of time. So that's hopefully one of the things that we know is going on in the industry is they're trying to work out leaching tests, and in fact, McGill University is somewhat involved in trying to determine longevity. But generally, if you look at some of these EPA extraction methods and look at TCLP and different pHs, that will give you a sense of the longevity.
Okay. And we got one final question from Kurtapol, who asks, can you comment on the mechanical strength or hardness of the FLUORO-SORB media? I guess that relates to the fact it's a sheet-like material, suggests it could be quite fragile.
Yes. Generally, well, it's a powdered material, and if you put enough energy into it, you can break it down into smaller and smaller sizes. So it's not like an ion exchange resin. So if you're handling it into a vessel, there is the opportunity of generating fines, and generally when you fill the vessel, you'll backwash it to remove anything that you've generated. In terms of in situ stabilization, one of the really neat things that we found that was completely unexpected was when you do molded soil cement samples and you do a strength test on the monolith, that FLUORO-SORB actually improves the set strength a little bit. It's not, game changing, but we do see a statistically significant increase in the set strength with FLUORO-SORB. So, which means you might use a little bit less cement for your particular mix design.
Okay, there we go. And the final question from VJ was just, will a recording of this presentation be available? Yes, if you just hold on to the URL of this, the link in the top of your screen, after we finish the broadcast, about 10 minutes later, the recording will be available for you to watch back. So don't worry about that. Okay, that's all the questions we've had. So I just want to touch back on that. Prior to today's webinar, were you aware of FLUORO-SORB as an effective PFAS solution? And 62% said no. So there you go. They're certainly aware of it now. So a big thank you to our three speakers, to Chris, to Mike, and to Mike. It's been fantastic. I'm sure on behalf of the audience, we'd like to thank you for giving your views and perspectives and giving up a bit of your time, especially because it was so early there. So thank you very much for that. Before I go, I just wanted to remind everyone who wasn't able to attend our Brownfield Summit last month that you can watch the summit and all the presentations and slides on demand. Click on the green button at the bottom of your screen that's just appeared there, and it will take you to that. And Meredith has asked, could you please share the final slide with our contact information? Yes, I can, but I will have to boot someone off. Mike, are you happy to go?
Okay. No, I'm fine. Thank you.
So there you go. Mike's gone. So I'm just going to share this so everyone has the final contact information. We don't want anyone to not be able to get in touch with these guys because, let's face it, they've got some good solutions. So there you go, CETCO@mineralstech.com. Right, as I was saying, so yes, if you would like to watch any of the Brownfield Summit recordings, click on that green button on the bottom of your screen, and you'll be able to essentially book on-demand replays of that summit. I also want to point everyone to our fourth COVID-19 in the Brownfield community discussion next week on Tuesday. My colleague Ian Grant is going to be joined by Neil Hutchinson, the Managing Director of Geosciences at RSK, George Evans, the Managing Director of Soilfix, and Pat Hayes, the Managing Director of BeFirst. That's going to involve a really good discussion about how to get people back into work in the brownfield sector. Bear in mind what we've all experienced over the last few months. We will also be having an innovative networking platform where essentially you'll be able to integrate face-to-face with other members of that audience and share your experiences and talk face-to-face and rekindle a bit of that live networking that we've all been missing. So that is on Tuesday. You can find details of that on our website. So we look forward to seeing you then. Other than that, goodbye from myself and from our two speakers, and thank you for watching today.